So very good afternoon to all the viewers this afternoon. We have this live interaction session in the NPTEL course on digital signal processing and its applications. And I'm very happy to welcome all the viewers who are with us this afternoon. This live interaction session is meant to discuss anything that you wish to pertaining to the course or anything that you wish to as a student discussing with a faculty member and other students. In fact, I'll just shortly introduce my young friend here. So this is a session where you could interact with us at IIT Bombay under the NPTEL framework. Please make the very best of this live interaction session. I believe that this course will soon conclude. I do not think that we'll be able to have any more live interaction sessions in this course after this one. So please make the very best of this session. Now, of course, I suppose some of you would know me because you must have seen the lectures. I'm Gadre. I'm a professor in the Department of Electrical Engineering at IIT Bombay, and I've been the instructor for this course on digital signal processing and its applications. And I have my young friend here sitting with me, Puranjay Datta, who's one of the teaching associates. You might have occasionally seen him respond on the discussion forum. And today he's here live and breathing before you.
Hi everyone.
You can introduce yourself, Puranjay.
My name is Puranjay Datta and I am currently dual degree student in IIT Bombay, and I am pursuing CSP, that is Communication Signal Processing, as my MTech specialization.
Very good. So Puranjay is in the 4th year of his dual degree. Dual degree means BTech plus MTech program. It's a 5-year program, electrical engineering. And his specialization in the MTech program is in communication and signal processing. Puranjay was one of the students who did very well in the course on digital signal processing when it was taught to them almost more than a year ago. And he then opted to assist us in the conduct of this course. And today, in spite of the fact that he has his semester and examinations going on, he has consented to come and be with all of you in person. So we must all welcome him very warmly. And I'm very happy to see that we have a few people. So I can see there's somebody from OM Academy saying good afternoon. A very good afternoon to you. Would you like to introduce yourself? I'm sure you have a name beyond OM Academy. And also we'll start taking questions. So yeah, we have a number of questions lined up, so I'll take them one by one. So while you introduce yourself, let's see. So I have questions here. Kind request to explain how to solve first assignment question in assignment 5 and also assignment 12. Okay. Assignment 5 and also questions 5, 9, 10. XM troublesome input case. Definition of okay. Okay, why is this? Okay. All right. You should spell out the assignment. Don't simply give the assignment number, right? Spell out the assignment. Say, I mean, it's becomes very difficult to answer the question like this when you say, please answer. I don't remember offhand which question you're talking about, and it's difficult for us to keep scrolling. So what you could do is you could ask us specifically what questions you have with respect to that assignment problem, and we'll be happy to answer it. Okay. And yes, I mean, okay, so in Home Academy, I see that there's Hemantika. So welcome, Hemantika. And you're a PhD scholar. Very good. We are happy to have you with us this afternoon in this discussion. And So what I'll do is I'll begin by taking up this question, which is clear. You know, it says in Xn troublesome input case, definition of Xn conjugate H Maya. See, let me explain that idea once again. So I'll use the whiteboard to explain. So I'm hoping that all of you are able to see the whiteboard. Now, you see, the idea there, when you want to, the so-called troublesome input, which we are talking about, I'll just explain that. The troublesome input, which we are talking about, is the input which forces the absolute sum of the impulse response to emerge. So, it's to be. How do we go to the next one? I think. Okay, so how do we go to the next slide? Oh, yeah. This one? Yeah. So you see, if you look at the output, y of n is summation over all k integers from minus to plus infinity, xk hn minus k. This is in general the input-output relationship of a linear shift invariant system. This is the impulse response. And this is the input. This is the output. Now, in particular, we take n equal to 0 here. Let's force the impulse response to come as an absolute sum at n equal to 0. So what would happen? You would get y of 0 is summation over all k, integer k, xk h of minus k. Now you want this to be forced. You want this to be forced to become the absolute sum of the impulse response. So what would you do? Let's write it down explicitly. So your y of 0 is summation over all k integer xk h of minus k. Now what you need to do is to choose xk so that you make h of minus k into the absolute value, right? So make hk, or rather h of minus k, assume its absolute value. So how would you do that? Essentially, multiply it by exponent minus angle of h of minus k, isn't it? Look at the angle of the sample. If it's a complex sample, look at the angle of the sample, not the magnitude. The magnitude is already there. And essentially multiply it by essentially remove the angle. That's what you want to do. Now, removing the angle is meaningful if that sample were inherently non-zero. If the sample is 0, then of course you don't need to do anything at all. The magnitude is 0, so let it be where it is. So you can just take xk equal to 0. But if the magnitude is non-zero, then you essentially choose x of k to multiply by the exponent of minus the angle. That is what you're doing here in this so-called troublesome input. Yeah. So the troublesome input that we are talking about here is essentially to multiply. So the troublesome input converts h of minus k into mod of h of minus k. And the summation, of course, ranges over all integer k. And it doesn't matter whether you're running minus k over all the integers or k over all the integers. So that's what you're really doing in this question. I hope this clarified your doubt. If not, and if you're there, could you please come on live and say what is not still clear? I hope this clarifies the doubt. Let's stop sharing this. So I hope this clarified the doubt of that gentleman or lady. No, it was. Can we have a response whether it clarified? Anyway, while the gentleman or lady responds, I believe I'll just say, who it is. It is Deshik. Oh no, this is somebody else. Tilak man. No. Tilak Marupilla. Tilak Marupilla. That is the person who asked this question. So anyway, let's take up the next question. So is there anybody who would like to ask a question live? We'll also try to take some of the live questions. So now, Hemantika, since you're there, you're asking us to solve assignment 12 questions regarding 5. See, this way we would not remember the questions. Can you put the questions here on the chat or something, then we can try and address what you have in mind. We are, of course, trying to look up the site, but then, it'll be better if you identify what is specifically troubling you there. Yeah, you can log in. You can log in or anyway, we'll see what. Let's go to that chat window itself. So yes, so Ivantika, would you like to say what is specifically troubling you in that question? Then we can try and address it. Meanwhile, while you type this, it'll come on the chat window. I'll look at the other questions. So we look at that. Yeah. Now I have one question from a faculty at bits. I can see kgk.bits bits. It says concept of negative frequency on x-axis and why we choose zero-centered signals when time is always positive. You see, time always moves in one direction in physical reality. I do agree with you. But that does not mean that you cannot have a reference at a point in time and then look at times before that and after that. A simple example is that we identify a so-called 0 year, isn't it? We identify a 0 year when we write down the calendar. So we are saying the current year is 2023. 2023 after that 0 year, which we've identified in the current calendar, in the calendar that we follow, isn't it? Or so there is the so-called Vikram Samvat calendar which we follow, which has a different reference. This is a Gregorian calendar which follows a 0 year and which brings us to the year 2023. So there are, of course, that does not mean that you do not have years before the 0 year. Of course, you have years before the 0 year. In that sense, time is endless, isn't it? So therefore, you can have negative and positive values of time with respect to a reference. That's what it means. So while time assumes to move in one direction, you can choose a reference, and with respect to that reference, you can have time before that reference and after that reference. That's how you should understand it. Yes. So I hope that clarifies the question here. Why we choose zero-centered signals when time is always positive. Okay. Well, I have one comment from Samadhan Kulkarni, who says there's no question, but if there's no question, there's nothing I can answer. So anyway, let me take another question which I have here. A student asked the question, other than FFT and autocorrelation, what are power spectral estimation methods used currently? See, what is power spectrum estimation? First, let's look at that, right? So what is power spectrum estimation? Power spectrum estimation means estimating mod of the modulus square of the frequency of the Fourier transform. Now, where does the problem come? You see, you can never really calculate the Fourier transform from a limited part of the signal. That's where the challenge comes in power spectrum estimation. You can at best take a segment of the signal, find out its Fourier transform, and you can keep doing this for various segments and take some average, and then you could assume that that gives you a good indication of what the Fourier transform looks like. So now when you say that FFT and autocorrelation are two different ways, let me explain what you're doing in each of those ways. In the autocorrelation method, you recognize that the power spectrum or the modulus square of the Fourier transform is really the Fourier transform of a time domain quantity called the autocorrelation. So you take the signal and you shift it by different amounts, and you essentially take the dot product of the original signal with the shifted signal, and then you take the Fourier transform of these dot products, seen as a sequence in its own right. Naturally, you cannot really use the whole signal. So you use segments of the signal and take the dot products of with shifted versions of the segmented signal. And then you assume that this is reasonably indicative of the magnitude square of the Fourier transform. The other way is you calculate the Fourier transform directly and take its magnitude squared and then average. So, there are different possibilities there. You could first take the FFT, take several FFTs of different segments, average these, and then take the magnitude squared. Or you could take the magnitude squared in each of these FFTs and then average those. All these are really approximations. You could also window. See, the moment you're cutting the signal into segments and you're taking its Fourier transform, it's not really representative of the actual Fourier transform. So what would you do? You could segment the signal, multiply it by a window and take the Fourier transform. This is called a windowed Fourier transform. Or, it's a windowed approach to time frequency estimation. So all these power spectral estimation methods are really different approaches to visualizing what the magnitude squared of the Fourier transform of the signal might look like. But, you can never really do it with complete accuracy because you can't see the signal all at once. Okay. I'm not sure if this is what you had, in mind when you asked the question. But if not, if you're around, please let us know if you have a further question on this. Now, I think there's some, Himantika has put up something in the chat. Let's see. She said some, okay. Assignment 12, okay. A butterfly is a part of, okay, she's putting up. Butterfly is a part of a fast Fourier transform algorithm. Please explain with how to find twiddle factor. Okay. All right. So let me explain what this twiddle factor is. So let's take the twiddle factor. See, in the fast Fourier transform, for that matter, in a discrete Fourier transform, which we write like this. We'll write the discrete Fourier transform, x of k. The x of k is the discrete Fourier transform of x of n. Xn e raised to the power minus j 2 pi by n times nk. N going from 0 to capital N minus 1, where there are n samples or n points in the sequence x of n. So this is the discrete Fourier transform. And of course, k also takes the values from 0 to n minus 1. This is the DFT. Now, the twiddle factor idea comes from here. This gives rise to the twiddle factor. So, essentially, if we denote e raised to the power minus j 2 pi by n as wn, then what we are saying here is effectively capital X of k is summation n going from 0 to n minus 1 xn wn to the power minus nk, or rather plus nk, because you've taken the minus sign here. Now, wn to the power of k in general is called a twiddle factor. What does this twiddle factor do? The twiddle factor adds only to the angle, not to the magnitude. Its magnitude is 1. It's essentially a rotation of the complex number. So it rotates the complex number to which it is subjected. And the reason why it does that is that it's a step in finding one of the components of the DFT. So if you recall, I'll just show you perhaps one so-called butterfly, which you're talking about there. You might recall that, in the so-called butterfly, which you're talking about in the FFT, you have this structure. Like, for example, in the decimation in time approach. And prior to this, you have a twiddle factor placed here. The twiddle factor prepares the prior computation to be subjected to this, what is effectively a 2-point DFT. The so-called butterfly that you're talking about is actually a 2-point DFT here. So if you look at it, the broader way of understanding this is that when you're trying to construct a fast Fourier transform algorithm, you are effectively breaking up, you're doing a divide and conquer. That's what you're doing. You're doing a divide and conquer. So you're saying, for example, if you had an 8-point discrete Fourier transform, then you're breaking it up into 2 4-point discrete Fourier transforms, followed by some additional computation. And to complete this, you need to do, so you're breaking it up into 4-point discrete Fourier transforms and a residual 2-point discrete Fourier transform. That this residual 2-point discrete Fourier transform is what you're calling the butterfly. And the additional computation that you need to do to achieve this is what results in the twiddle factors. Of course, then that 4-point discrete Fourier transform again breaks up into 2-point discrete Fourier transforms followed by some additional computation. So you keep getting twiddle factors with lower number of points as you keep doing this breakdown. So with the 8-point discrete Fourier transform, you break it into 2 4-point discrete Fourier transforms and then 2-point discrete Fourier transform, which you're calling butterflies. But interspersed between these, you need to have the twiddle factors, which join the 4-point discrete Fourier transforms to the 2-point discrete Fourier transforms to complete the computation. That's another way of understanding this. So I do hope that you understand the meaning of the twiddle factor now. That's Hemantika, I think. Is that right, Hemantika? So please, you can put your message on the chat window to explain whether you understood the meaning of the twiddle factor. If not, you can ask further questions. Now, let us see if there are some questions from the chat which we can address. And meanwhile, you can also, people can put up their questions in the chat again. Let's see the chat again. Chat. No, this is chat. No, let's see the Excel sheet. Yeah, that one. No, the other one which you showed. Yes, that one. Yes. How to find dash values? There's a question. How do you this? Assignment 12 seems to be challenging to everyone. Let us see what that assignment 12 is. Let's see. We'll try and locate what is assignment 12 that all of you are troubled about. If we can identify what they're talking about, then we'll try to see if we can help them. Meanwhile, people can put up their questions in the chat while we try to find out what is troubling you in these. Okay, so Himantika says she understood what the twiddle factor is. Meanwhile, you can put up more questions in the chat while we try to figure out what your problems are with assignment 12. There's a question for 5 to 8, whatever those are. Question, do we read them out? Okay.
So we have two sequences.
So I'm trying to figure out what your questions were. So let us, so it says you have two sequences, xn and hn, and then you're required to find xn, which is 5. X.
It's just shifted.
In fact, Puranjay will now help you, I think, with this, right? So, in fact, Puranjay, if you wish, you can sit here. You can come here. I'll this way. We can exchange. Yes. So I'll ask my young friend to help you with this assignment. Go to share, and then go to PPT. Yeah, PPT, share. You go to the next page. Yeah. You can use this pen and write on the.
So this is like just a notation of the sequence. By this arrow, we mean that the reference point of the sequence is at position 3. So basically in x dash n, we just want to shift the sequence by 2 positions to the left such that the arrow comes here. So the new sequence becomes and so the answer is A and C, where x dash of 2 is 1 and x dash of 3 is 2. So answer is A and C. And similarly do for h of n also. This is like just a notation for the reference point of this sequence that we take.
So I hope that clarifies this. Anyway, please put up, if you have further questions, please put them up. And in assignment 12. And then we had some other questions as well. So have we addressed your questions? If otherwise, please put up your queries in the chat. How to find dash values. So that I think has been addressed.
And similarly for question 7, we have been given y is equal to x prime circular convolution with h prime. And so we know that there is a matrix form of writing circular convolution as y is equal to m times h prime, where m is some matrix which involves x prime. So x prime was minus 3, 4, 1, 2. So we get m as -3, 4, 1, 2, and then rotate it cyclically for all the columns. So we get 2, -3, 4, 1. Then we take 1 up. Then 1, 2, -3, 4. Then 4, 1, 2, -3. And we need to find the trace of the matrix as the sum of the diagonal matrix. So this was the question.
Oh, so I hope we've addressed your question. Stop sharing. So I hope we've addressed your question. Are there any other viewers and would they like to put any other questions? Can we find out how many viewers we have currently? Okay. Scroll up. This one? This one? You come. 11 watching. So we have 11 people watching. So I'm very keen to have some of them maybe this screen. So then that means that we have several people watching the session. So why don't you people put up questions or, why don't you put up something in the chat? Because we can't, can we allow them to talk? We can't allow them to talk, no? So then the only thing we can do is to listen to you in the chat. So you have to put up something in the chat for me to be able to respond. Because whatever questions I got in the Excel sheet, I've already discussed the solutions. If you're not clear with those solutions, please respond in the chat and I can further elaborate or we can, further clarify for you. But you'll need to put up something in the chat to take this discussion further. Yes? So. Oh, okay. Sorry. Yeah, sorry. There are plenty of questions which I can see now. Yeah. Okay. Vaishali Pandey is asking why FIR filter is preferred over IIR. Okay. See, I won't say FIR filters are preferred. FIR filters have some distinct advantages. FIR filters are unconditionally stable. That's one thing. FIR filters can give you linear phase, right? FIR filters can give you linear phase. They don't have to give you. I mean, you can have an asymmetric impulse response in the FIR filter, then it will not have linear phase. But FIR filters can be designed to give you linear phase if you're willing to go for a longer length, right? Because you have to then take samples on both sides of 0. But FIR filters can take care of phase response. So those are the positive sides. The negative side is that FIR filters typically require more resources to realize. So that means that for the same specifications, the FIR filter would typically require more resources to realize. And that is a disadvantage. So I wouldn't say FIR filters are preferred, but I would say that there are these strong advantages of using FIR filters, namely stability, unconditional stability, and possible linear phase. Also design for FIR filters, there are very simple approaches to designing FIR filters using windows. And there are also more complex approaches using optimization methods. For IIR filters, designing also is a little more non-trivial. In the sense, one needs to actually take advantage of the designs known in analog filters and then transform them to discrete time. That's one approach. The other approach is again to design by optimization. Whatever it is, designing IIR filters sometimes poses more challenges than designing FIR filters. But then if they, notwithstanding all that, having designed the IIR filter, it would probably be realizable with less resources. So nothing comes without a cost. And also, when you put in a cost, you do get benefits in some sense. So therefore, I won't say that there is a unilateral decision in favor of FIR filters, but yes, there are several reasons why people prefer FIR filters. Now, in fact, I have several other questions. I'll take them up one by one. Gopal Krishna Koneru, I hope he's on the chat right now. He's asking one general question. Generally, when we want to represent message signal, we indicate in illustrations and textbooks that as triangle in frequency domain. But can the message signal be of any shape in the Fourier domain? See, there is a reason why we choose that triangle shape. It is the simplest shape which has a different frequency response at every point, different magnitude at every point. The simplest example of a shape which has a different response at every point. Moreover, when you want to combine two such triangles, it's easy to add them and so on. If you use any other shape, then writing a general expression for the summation and so on will be more complicated. Here, when you're adding two straight lines, it becomes a straight line, and that's easy to visualize. So therefore, we use triangles as prototypical spectra to analyze aliasing and so on, simply because it's the simplest example of a Fourier transform where you have a different value at every point. So there is a one-to-one correspondence between the point and the value. And you can combine shifted versions of this triangle very easily. But of course, a triangle is only a hypothetical kind of Fourier transform. Naturally, realistic signals would have very different kinds of Fourier transform. I hope that answers your question, Gopal Krishna Konaru. And then Gopal Krishna is also asking, can we say modulator, say amplitude modulator, multiplying signals in the time domain, an LTI system? A modulator is not LTI, right? It's linear, but not time invariant. It's very simple. The reason is very simple. If I shift the signal, what results from modulation is not a shifted version of the original signal, or original output. So modulation, amplitude modulation is a linear process, but not time invariant. So although you can analyze it spectrally, that should not lead you to conclude that it's linear and time invariant. Yeah. We know filters are considered as LTI systems. But modulators, if you talk about the amplitude modulator, it's a linear system, but not time invariant. Now, I have Himantika from Home Academy asking, or somebody else asking, find the trace of matrix M subject to Y is equal to MH prime. Explain, please. Well, I think we just explained that was the question, right? So see, the trace of a matrix is the sum of its diagonal values. The trace of a matrix is the sum of its diagonal values. Maybe Puranjay will now give you an example to find the trace of a matrix.
Like this was the same question in the assignment. We had to find matrix M such that it represents the circular convolution of X prime and H prime. So we are given X prime. We just need to circularly rotate it every column such that it gives this matrix M.
Yes.
And we need to find the trace of this matrix, which is the sum of its diagonal elements, that is -3 plus -3 plus. And that's all.
So as you can see in this case, the trace of the matrix, in this particular case, where you're circularly rotating the rows, the trace would really be 4 times or whatever the size of the matrix, that many times a particular element which occurs, right? In this particular case, when you have the circular rotation of the rows. In general, the trace of a matrix is the sum of the diagonal elements. And of course, the trace of the matrix also has other significances, right? It has a significance regarding eigenvalues. If you set up the eigen equation for a square matrix. The trace of the matrix is very important there, right? So we'll be, it's anyway. Let me take the other questions. Is that clear, Himantika, what trace means? Now, yes. Gopal Krishna Ponaru was asking, can frequency scalars, multipliers, be said as non-LTI systems as they change the frequency? Yes. When you multiply, see, for example, suppose you were to square a signal. It's an example of where you do frequency multiplication. You're multiplying the frequency by 2. For example, if you subject a sinusoid to squaring, it will have 2 components. It will have a double frequency component and a 0 frequency component. So here, this is an example of a non-linear shift. It's a non-linear system, of course. So the other possibility is, you could shift a frequency. You can shift a frequency by multiplying by another sinusoid. That's what you do with amplitude modulation. In amplitude modulation, it's a linear process, but it's not shift invariant. So you have both possibilities. You could have non-linear but shift invariant processes. For example, if you square a signal, it's an example of a non-linear operation, but it's shift invariant. And it does double the frequency, it multiplies the frequency by by 2 or whatever. If you cube, if you take the cube of a signal, it's an example of a non-linear operation but shift invariant. And there, you're bringing in 3 times the frequency. On the other hand, you can take the operation of modulation, multiplication by a sinusoid. That's a linear operation, but not shift invariant. That shifts the frequency. So both of these are examples of non-LTI systems. In one case, linear, but not time invariant. In the other case, time invariant, but not linear. But you're very right in noting that if you wish to shift on the frequency axis, or if you wish to multiply the frequencies present in the signal by a factor, that cannot happen with a linear time invariant system. Correct. So Vishal Verma says he understands. And Himantika also says that she understands. Now, let's have more questions in the chat. Let's have more questions. We have 10 minutes more in the session. Maybe while you put up your questions, you can also introduce yourself. Oh, that's a good question. So I have Gopal Krishna Koneru asking, thank you, sir, but FM modulator is LTI. FM modulator is not LTI. See, what is a frequency modulator? In fact, the frequency modulator is highly non-linear. What are we doing in frequency modulation? We are changing the argument of the sinusoid in the carrier. In fact, you're not only changing the argument, that argument contains the message. That's a highly non-linear operation. Now you may ask whether it is shift invariant. So what does that mean? If I shift the message by a certain time, would the output be shifted by the same time? Well, depending on how you do the frequency modulation, you can make it shift invariant. You're right. So, for example, you can say, I'll use the board here. So, if you, for example, suppose, so, if you have x of t, let's say, as an FM signal, something of the form, let's say A cosine, there's a carrier, say omega ct, plus there's a message signal. So let's say, for example, so you have, let's say, so let's take a very simple case of an FM. This is a very simple case of an FM, with some modulating parameter B, a very primitive FM. So here, what have you done? I mean, this is a principle of FM, frequency modulation or phase modulation. Here, actually, you're doing phase modulation because you're modulating the phase in accordance with the message. If you're modulating the frequency, the derivative of the phase should be equated to a multiple of the frequency. Anyway, whatever it is, if I shift mt by some time, so suppose I replace mt by mt minus tau, would you get xt equal to xt minus, would you get xt minus tau here? No, not in general. So mt being replaced by mt minus tau does not result in xt being replaced by xt minus tau. Why is that so? Because you have this term, omega ct. So when you replace t by t minus tau, when you replace mt by mt minus tau here, you're not replacing omega ct by omega c into t minus tau. That should be noted. Yes. So in that sense, it's not shift invariant. But if you were not to have this term, omega c into t, then the rest of it would render it shift invariant. But then that would, that would have no, I mean, you have no carrier there. You are doing frequency modulation in the base band. That's not helpful, right? So if you wish to move it to a carrier, then you're losing the shift invariance in frequency modulation. Of course, needless to say, frequency modulation is highly nonlinear. Highly nonlinear. You can see that if you take a sum of two messages there, it's not going to result in the sum of the two FM signals. So FM is highly nonlinear, right? So it's normally both nonlinear and shift variant, not time invariant. Now, I also take his next question. By looking at the impulse response, how can we say it is a signal or a system? No. I'm not sure what the question was. Gopal Krishna, would you like to clarify? See, signals and systems are fundamentally different. See, signals are really mappings from the indexing variable to the value. And systems map signals to signals. Signals, in some sense, systems are mappings from signals to signals. And signals are mapping from the index to the value. So an impulse response is an example of a signal. An impulse response is the example of what signal emerges when you give a particular input to the system, which is what we call an impulse. That means if you're talking about a discrete sequence, discrete system, there's no problem because you just give a 1 at n equal to 0 and give 0 everywhere else and look at the output. That's the impulse response. For a continuous time system, it's more difficult to explain what an impulse response is. You visualize a very narrow pulse around 0 and give that as the input to the system and see what the output is. That is the impulse response. Yeah. So, Gopal Krishna, but both look the same, Xn and Hn. I'm not sure. Would you like to explain? We have not understood what you're trying to ask. Okay. All right. Now, Himantika from Om Academy is asking Xn equal to -1, 2, -3, 2, -1. The value of x e raised to the power. So the discrete time Fourier transform times squared. Okay. Explain with integration value. d omega. Oh, x e raised to the power j omega. Oh, I see. It's mod squared. Okay, I think essentially yeah. I think what Himantika is asking is this. Yeah, I think what Himantika is asking is x e raised to the power j omega mod squared, or is it just squared? Okay, just squared. Okay, just squared d omega with respect to omega. Now, how would you do this when you square the Fourier transform? This is the DTFT of xn convolved with xn. So you convolve xn with xn, convolve it with itself, and you're obtaining and you're integrating this with respect to omega. And you see, you would find the inverse DTFT here. You know, if you want to put the inverse DTFT here, you would add the term e raised to the power j omega n. But if you put n equal to 0, then this simple integral would result. So essentially, you must find out what is xn convolved with xn evaluated at n equal to 0. So convolve xn with xn at n equal to 0. That's the value of this integral. Is that clear, Himantika? That is, in general, how you do this question. Now, Vaishali Pandey is asking, what is the application of lattice structure for digital filters? To capture the answer in just a couple of sentences, the lattice structure, the word lattice means a uniform repetitive structure. So the lattice structure is a uniform repetitive structure which can realize FIR and IR filters. It's a modular structure which can be repeated. But that's not the only reason why you build lattice structures. The lattice structure enables you to monitor the stability of the IIR filter. So essentially, when you look at the lattice parameters, if and only if the denominator has all its zeros within the unit circle, the lattice parameters in the lattice realization of the IIR filter would be less than 1 in magnitude. So to check whether the IIR filter is stable, you look at the lattice parameters in the realization of the IIR filter with a lattice structure. All the lattice parameters need to be less than 1 in magnitude if the filter is stable. That is the reason why we use lattice structures. Do we have more questions? Yes, I can see that Gopal Krishna Kunal has understood the answer, and I also see that Himantika has understood. Good. So Vaishali Pandey, is it clear? Okay, now let me see. There's one question. I have an academic gap 8 after MTech. Will I be eligible for PhD? Bhuvanesh is asking. Well, Bhuvanesh, would you like to tell us more about what you're doing currently and what you want to do your PhD in what you want to do your PhD, what subject or what theme? I don't think eligibility, if you have got an MTech by itself is an eligibility for PhD. I think you need to have a first class in MTech that's required. But would you like to tell us more about what you're doing currently and what area you want to do your PhD? Having an academic gap, so to Bhuvanesh, academic gap is not a disqualification for preparing for competitive exams. Interested in signal processing. Okay, very nice. academic gap is not a disqualification for entering the PhD program, but you need to have a first class in MTech and you need to clear our entrance procedures for PhD. So I'm not sure if you applied for the PhD. You have to apply formally for the PhD program. Have a gate score, okay? But that gate score must have been used for your MTech program, isn't it? That's anyway, if you have an MTech, the gate score is not needed. If your MTech is with satisfactory performance. And you need to clear our admission procedures and be selected for the PhD. So, it says, sir, I cannot find the course name in exam Excel sheet. I don't know how to. Yes, Bhuvanesh, wish you all the best in following up with your desire to do PhD. Well, why can't you find the course name? It should be there in the exam Excel sheet. Are you looking at the right Excel sheet? There might be a different Excel sheet for the 12-week course and for the 8-week course. And, there are different courses. Some of them are only for 8 weeks. Some of them are for 4 weeks. Some of them are for 12 weeks, 1 month, 2 months, 3 months. So maybe you're looking at the wrong Excel sheet. Just check. Different name. Are you looking at the Excel? Are you looking at the list of courses which are for 12 weeks? Then you should write to NPTEL. They've given an address, I think, where you can write to and ask them. It should be there. The course should be listed. Since you're able to see this session, the course must be listed. So then, okay. Okay. All right, so we are past 5 p.m. now. If there are more questions, we can continue this discussion, but if there are none, then we will bring it to a conclusion. If there are anything else that anybody wants to, we can continue if there's anything more that somebody wants to discuss. So does anybody want to discuss anything further? Does anybody want to comment anything further? Okay, I don't see any further inputs from the chat. So therefore, we will then bring this interactive session to a close. I'm very happy that all of you participated very actively this afternoon in the interactive session. Thank you for being with us this afternoon. Very glad that we have live interaction from all of you, which I'm sure will benefit many others in this course as well. And otherwise, do keep up the enthusiasm in understanding the subject. And, I look forward to seeing some of you in person sometime. Wishing you the very best. And also on behalf of my young friend, he'll also say a few words as we conclude.
So I hope you learned something from the course, and I had a great time being a teaching associate for this course. And I hope you will pursue signal processing or some form of it in some form or another. Yeah, that's it from me.
Very good. So as I said, Puranjay should be lauded because he's come here in the middle of his semester and examinations, and he's come. That shows you the enthusiasm of my teaching associates. And I'm sure that the enthusiasm of our teaching associates is also reflected in your enthusiasm. Yes, so wish you all the very best, and we'll conclude this session.